All right, hello and welcome to your lesson on chemical bonding. We're going to go into ionic bonding for this lesson. Okay, so here we go. Atoms bond to form a molecule. So the way that atoms are attracted to each other to form molecules determines nearly all of the chemical properties that we see in all the things and substances that you come in contact with. And as we will see, the number 8 is very important. So think back to that octet rule that we learned about. So very important for chemical bonding. A chemical formula is how you write out what is in the molecule. And you've probably used this yourself. H2O, for example, that's how you write a chemical formula, H2O. So we use the element symbols like H and O in this instance, and the numbers to indicate their amounts, kind of like ingredients in a recipe. So here's that example again. So after each chemical symbol, you would put in a little subscript to indicate how many of each there is. So in this molecule of H2O, or water, you have one O and two H's. So you would put in a little 2 for H2, as in you have 2 of those, and you don't put in a 1 when there's only 1 of something, because the fact that O is written at all, you know there's at least 1. So we like to be efficient in science, so we kind of skip over things that don't need to be said. So the fact that O is written at all, we know there's 1 of them. Okay. All right, so let's practice for a moment. Write out the chemical formula for this caffeine molecule, one of my favorite molecules, and use this key below to help guide you a little bit. So note the colors of each of the elements inside of the molecule and put in the subscript of what belongs in each element's subscript. Okay, pause me if you like, but I'm going to move forward assuming that you pause to take your turns to try things out. So for this one, carbon is black according to our key. So I'm going to count out the black molecules. Don't forget about this one. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. So I would put an 8 right here. H's, okay. Hydrogen is white. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I would put a little 10 right here, subscript. N you would have is blue, so 1, 2, 3, 4 N's, so there's a little 4. And then oxygen, nice and easy, we only got 2 reds, so 2 oxygens. So hopefully you filled that in and checked your answer with me, and you've just written your first chemical formula for a relatively complex molecule. All right, let's try out the chemical formula for aluminum sulfide. And notice I changed the ending of sulfur to sulfide. So hint, the order that you would write your formula in is the same order that you write the name in. So again, pay attention to this name to determine how to write out your formula. Who goes first? Okay, take a moment. All right, hopefully you've got AL written first because he's the first one written in the name, and S written second because he's the second one. There's 2 ALs, so you should have a subscript of 2 and 3 sulfurs, and this is what it would look like. Al2, S3. Okay, now let's write out the chemical formula for lithium oxide. Again, notice I've changed the ending to "ide." Oxide. So that would be, these 2 are the nonmetals that are starting to get this "ide" ending when they form a bond. So start to notice that. Okay, so here I see lithium, 1, 2, and there's only 1 oxygen. Well, what did I tell you about? If there's only 1 of something, you don't need to put a little 1 next to it. You just put the O, and we know that there's 1 there. We know that there's at least 1. So Li2O for lithium oxide. Okay, so bonds within molecules, otherwise known as intramolecular forces within molecules. Molecules are a combination of atoms bonded together. Bonding determines the chemical properties of the molecule. So depending on who's present in the environment, you might end up with an ionic compound. So metal and a nonmetal are called an ionic compound. Or you might end up with a covalent compound, non-metal, non-metal. So we're going to explore ionic first. And you might be wondering, well, what about metal-metal? Well, that's for a later class. We're not going to do metallic bonds in this course, but they do exist. We're going to cover ionic first, and then we'll move into covalent. Okay, so electrons and bonding. As you know, elements have different amounts of electrons or electron configurations. So the configurations are how they fill up those energy levels that we explored. So different configurations, so how they fill those up, mean different levels of bonding. Okay, so different strengths, different strengths. All atoms aim to have a full outermost shell. What does that mean? Well, for the grand majority of them, that's meeting the octet rule, so 8 valence electrons. So ionic bonds. So we're moving into just ionics. So when a metal bonds to a non-metal, metals, as you now know, like to lose their outermost electrons in order to have their next shell down be full and meet the octet rule that way. So their next shell down meets the octet rule for them. When they lose electrons, when they get rid of a negatively charged particle or two, that means that they've thrown off their ratio of protons to electrons. So if you get rid of the electrons, you're going to end up with more positive thing, more protons in your atom. That would give it a positive charge. So if you get rid of an electron, a negatively charged particle, you're going to form a cation or a positively charged ion. Non-metals, however, like fluorine and all of those over there on that side of the staircase, they like to gain electrons. They like to take them in order to fill their outermost shell. So they become what we call anions because they're adding negatively charged particles and therefore they're going to have an overall negative charge. Now, since metals transfer their electrons away, non-metals take, one becomes positive, the other one becomes negative, and as a result, they form a strong bond called an ionic bond. So positive and negative attract. Here we have an ionic bond with a somewhat complex little crystal structure here. So this ionic compound is called potassium sulfide, and it takes a lot of potassiums to make quite a lot of sulfurs happy, okay? So sometimes it's not always one metal and one non-metal making the whole molecule happy as in everybody met the octet rule. Sometimes it takes a specific number of each to fill the octet rule so that everybody's met the right ratio and everybody's full by transfer of electrons. So what we do is we really focus on, in order to figure out the molecule, is the least ratio, so the most reduced form of the ratio that you can find. So rather than saying potassium 14, sulfur 7, we say potassium 2, sulfur technically 1, even though it's not written. Because look at this ratio. It's a 2 to 1 ratio, okay? So we simply reduce it in the formula to a 2 to 1 ratio. Simplify things. Let me explain some more in the future slides. Okay, so here's a nice way to cut through all of the work that it would take to draw that whole molecule out and show how everybody matches up perfectly. We can use this information that you need to memorize or internalize, and it's called the charge trend. Okay, so please make note on your periodic tables, you need to jot down the charge trend, okay? So add this to your periodic table. So you guys already have the valence electron trend written across the top of your periodic table, or you should. 1, 2, 3, and so on, skipping this lower section, all right? So that should already be on your periodic table for my class. Now, using your logic, I want you to understand this charge trend rather than just jot it down. It's nice to have it there when you're doing a complex problem, but let's take a moment to understand why the charge trend works. Now, as you know, metals lose in order to have their next shell down be full and meet the octet rule. So let's say someone in the alkali metal family lost that 1 valence electron that they have sitting on that outermost shell. That means that they lost 1 negatively charged particle and threw off their ratio of electrons to protons by 1. So if they got rid of 1 negative thing, that means they have 1 more positive thing than negative things. So they would end up with a +1 charge, okay? Now, the alkali earth metals, they have 2 valence electrons that they need to get rid of in order for the next shell down to be full and meet the octet rule. So they're going to get rid of these 2 valence electrons, and as a result, they're going to throw off their protons to electrons by 2, which means they'll have 2 more protons than electrons, so 2 more positive things than negative things, so they're going to end up with a +2 charge. Now, in the past, you know, when we were just learning the periodic table and a few groups and things, I kind of ignored these transition metals, but we do have a few that we can work with bonding. So here's what you need to know about those. Ag would form a +1 charge, this group would form a +2 charge, and this group would form a +3 charge because they have 3 electrons to give. So they're on this side of the staircase, so they are metals, and they are going to lose electrons in an effort to fill their outermost shell, okay? So again, we kind of ignored this section in the past, but we can use these now with this little bit of information that I've given you here. All right, now let's look at the nonmetals. So fluorine, okay, so the far nonmetals. Fluorine and everything down, these are halogens, and they have 7 valence electrons. They just need 1 more, okay? So they're going to take a negatively charged particle in order to fill their outermost shell, and therefore they're going to get a -1 charge because they took on 1 electron, 1 negatively charged particle. So now they have 1 more electron than protons. Oxygen and everything down, they need 2 to fill their outermost shell. So they're going to gain 2 electrons to fill that outermost shell, 2 negatively charged things. Nitrogen and phosphorus, they're going to gain 3 in order to fill their outermost shell. Now this column I've kind of told you to ignore a little bit. They would form a ±4. Oops, glitch. Thank you. Okay, they would form a ±4 in the event of bonding in this way. But we're not going to really work with these so much. The staircase cuts that group right in half. So we're going to just practice this skill with these more obvious families for now and groups. And as you get more in depth in chemistry, you can explore this group. And then of course you have the noble gases, which they have a 0 charge and they have no interest in bonding with anybody. So they're not going to form a charge. So there's the charge trend for you. Be sure to document it in your periodic table so that you can reference it without thinking through so much when you're doing a long series of problem solving. Okay, so there's how we document Na+. You would end up with a +1 charge. You guys have seen this ionic symbol here, this charge symbol. So hopefully it's starting to look familiar. You can put plus or +1, but again, if plus is written, you know at least there's a +1 charge. There's -1 chloride ion, so everything in this column would form a -1. Everything in this column would form a +2 charge, so that's how that looks. Plus or -2, +3, -3. So that's what they all look like when you write them up in ion format. Okay, so let's explore what this bonding looks like if you were to draw it out in a molecule or in a atom. Okay, so here we have sodium. There's his electron configuration drawn out for you. And there's that chloride atom and his electron configuration drawn out for you. Now, Na and Cl would react with each other because Na has 1 electron to give and chlorine needs 1 electron to take. So they will most definitely react with each other. And so both of them will meet the octet rule in one way or another. Might as well be sodium transferring his 1 electron to the chloride ion who needs it, who's now a chloride ion now that we've transferred that electron. So once that electron has given away his, once sodium has given away his 1 valence electron, now his next shell down is full with 8 valence electrons. So that, therefore, he has met the octet rule because his next shell down is full and now he's stable, so he's happy. All right, then we have chloride, who's now chloride now that he gained an electron. He took that 1 valence electron, so now his outermost shell has gained that 1 electron that he needed, and so now it's full and he's met the octet rule, so he's happy. All right, sodium becomes a cation, so a +1 charge. chloride becomes an anion with a -1 charge. There's sodium. He lost his electrons, so therefore the +1. Chloride gained an electron, -1. Positive and negative attracts. We've met the octet rule for both atoms, so we're done here. A little cheesy, I know. Got a little carried away with the animations on that one, but I'm kind of pumped about it. Okay. Ionic bonding of calcium fluoride. Ionic compound, calcium fluoride. Calcium has 2 electrons to give, okay? So how's it gonna affect the compound? Let's look at this. Calcium's gonna give 1 of his electrons away. He's a metal, he just needs to give away 2. So he's gonna find somebody to give him to, so his next shell down is full and he's met the octet rule. Fluorine needs 1. He doesn't need 2, he just needs 1. So once calcium gives 1 of his electrons away, he's gonna find somewhere else to give the other electrons. So he might bump into another fluorine, because where there's 1, there's probably 2. So again, we have to find the right ratio for everyone to be happy, because then they'll keep reacting until they are happy. So calcium will keep reacting until he can give away all of his electrons, and fluorine, among others, will keep reacting until they've gained all the electrons they need. So what it took in this scenario was calcium lost 2 electrons, therefore the +2 charge. Each fluorine that it took to make that calcium happy ended up with a negative charge apiece, because each one of them gained 1 electron. So ultimately it ended up being CaF2. So that's where we get the ratio from. How many does it take for everybody to meet the octet rule? That's where that magic number 8 comes in. All right, let's look at one more example. So calcium again has 2 valence electrons to give. And let's say this time he comes in contact with some chlorine. So the chlorine, they need 1 valence electron. So they've got 7, they just need 1 more. So the calcium will lose those 2 valence electrons, and then his next shell down becomes his valence shell, which is full with 8 valence electrons. So he's happy, he's full. Each chlorine gains 1 valence electron to fill the outermost shell. So since they've got their electron shell full now because they took that 1 that they needed, now it's full, it's met the octet rule. Now each of those chlorine atoms, now known as chloride, are now full, so they've met the valence electron or octet rule. So now they're happy. Since calcium lost 2 of its electrons, again, it got a +2 charge, so he's called a cation. Chlorine gained electron, so therefore he's got a -1 charge, so he's called an anion. Okay, so just repeat of the same vocabulary over and over again so that you start to use it yourself. It's absolutely insane to draw this whole thing out every time you want to figure out how many is it going to take to make the molecule happy, right? We don't want to do this every time, it's crazy. So here's a very efficient way to do it without drawing all the molecule out, because that's a lot of work. But it's good to be able to, so that you know you understand why. So for this, you're going to need your periodic table with your new charge trend written on it. So use that periodic table with your negative, +1, +2, +3, your whole charge trend written on it. Such a clever little trick. It's called the crisscross trick. So what you do, if you want to figure out, say, how aluminum chloride, aluminum and chlorine would react together, how many would it take for everybody to be happy? Well, this cute little trend, all you have to do is refer to your charge trend. You say, okay, I've got Al. What's his charge when he forms a cation? You look at your charge trend on your periodic table. Okay, well, he's a +3 charge, so you jot that down. Then chlorine, well, he's in the -1 column, so you plop that down. Then this magical trick, it's so amazing. You take that value, not the charge, but the numerical value, and you bring it down to the subscript of the opposite ion, okay? So aluminum's 3 would come on down to chlorine's subscript. Chlorine's 1 would come down to aluminum's subscript. That tells you how many of each you would need for this molecule to meet the octet rule and everybody be happy. However, when you write the formula for aluminum chloride, you know that you don't write 1s, right? They're redundant. So The fact that you read aluminum at all means that there's one aluminum. And then of course you need the 3 to tell us that there's 3 chlorines as opposed to 1. So there would be the formula for aluminum chloride without drawing out the whole big molecule. Kind of awesome. All right, let's practice a bit. Why don't you guys do this one with me? So take a moment. What would the formula be for the ionic crystal magnesium bromide? Notice me changing that ending to "ide" again. Bromide, magnesium bromide. Okay, let me give you a moment. Pause me so you can do it in your own time. Okay, now come on back. So magnesium, hopefully you found after referencing your charge trend on your periodic table, he's a +2. So you go ahead and jot down that charge right there. Bromine's in the -1 column, so there's that right there. You crisscross these values down. We don't bring 1s down because it's, again, repetitive. But you bring the 2 down to the bromine, so it'd be, oh, excuse me, MgBr2. The crisscross rule. So easy, so quick. All right, let's do the same for aluminum sulfide. Again, notice me putting the words together with an "ide" at the end, aluminum sulfide. Okay, so again, pause me so you can do it by yourself. Okay, welcome back. So aluminum has a +3 charge because I referenced my periodic table, and that's in the +3 column. Sulfur is in the -2 column. You crisscross those values on down. It's going to be Al2S3. Isn't that clever, neat, easy? Okay. Why don't you guys pause me right now and do these yourself? Okay, welcome back. I'm just going to plop down the answers. And you go ahead and check your responses. I hope you're noticing something in particular. This one right here says reduce, okay? We have Ca2O2, so it should be 2, 2, right? But we can reduce this value. Okay, that's the overall thing anyway, right? Remember the initial molecule, the crystal I showed you where it was like K14S7? You always want to reduce when you can. So since a 2-to-2 ratio is the same thing as a 1-to-1, just bring it on down to a 1-to-1. Okay, as opposed to a 2-to-4 ratio, you would just bring it down to a 1-to-2 ratio. So you reduce when you can. All right. I'd like for you to do these on your own, and we'll explore these after you do them in class as a do now during our next class period together. Remember, just a little hint, the name tells you the order of the formula. So whoever's first in the name should be first in the formula, okay? All right, so we'll come back to that during our do now next class period. Some general properties of ionic compounds. So some of these you guys know because you have table salt sitting on your table at home probably. NaCl is table salt, sodium chloride. It's a crystal, it's an ionic compound. It's the same stuff we've been doing. It's a metal and a non-metal bonded together. And it's a really clean cut one because it's a 1-to-1 ratio, so beautiful. It's really pretty up close too. It takes some time to look at it really closely. So they form these things called crystal lattice structures. They're crystals. They're very hard, they're very brittle. Again, you should know these things from your common table salt. Why does my computer do that? They have high melting points, so it would take a lot of heat to melt that salt on your table among all the other ionic compounds that we'll explore, and also high boiling points. So it would take a lot for those to boil. They conduct electricity as well, but only when they're dissolved in water. So that's an interesting thought. Think about that for a minute. How does electricity conduct in water? Well, it uses these positive, negative charges in the ionic compounds in order to conduct electricity, and we'll explore that more in a future lab, so something to look forward to. All right, well, that's it for today. Next time we will explore chemical bonding part 2, where we'll look at covalent bonds. But we'll leave that for next time, so I'll see you in class. Bye.